everyone. So with this example, we're going to do something slightly different, okay? And just a reminder that the other examples as well as the main lecture are linked for you in the description of this video. What we're going to do is we're going to try to figure out what the appropriate soil would be under a pad footing given some specific conditions. What we have here is some form of pad footing with a circular pier on top of it, and we're being told that the force coming down from the building up to the top of this pier is 163 kilonewtons. We have the geometry of the pier here. We have it as 200 millimeters in diameter, 1.2 meters or 1200 millimeters in height, and the pad measures 1,234 on each side by a thickness of 300 millimeters. Everything is in millimeters. The question is, what kind of soil should we expect to put under there to ensure that this building stays up, right? That this does not sink into the soil. And like I mentioned earlier on in the lecture, we're going to use a simplified method just using the bearing capacities that are found in part 9 under table 9.4.4.1. So the idea, as we've seen in previous example, is basically to balance out the force coming down on the soil with the resistance of the soil. But the difficulty comes from the fact that the force coming down is a force, right? There's the force from the building, and then the force we're going to figure out together from just the weight of the concrete, of the reinforced concrete. But somehow we have to balance that out against the bearing pressure of the soil, right? And what we found in the previous example, when we did that analogy of spreading peanut butter over toast, is that the bearing capacity of soil is over a unit area, right? So area is involved in this here, but it's not here. So somehow we have to balance that out. But I think before we go to balance this out, we should first find out what the force is just resulting from the weight of this concrete material, okay? And that's because for this specific example, you're being told that this building force coming down through the structure is up to the top of the pier. It does not include the weight of the pier and the footing. Okay, so let's find out what this force is as a result of the weight of the pier and the footing. Well, to figure that out, we basically have to find out what this weight is of that reinforced concrete structure. And the way to do that is first we have to find out what the volume is of that structure, and then multiply that volume by the density. Well, I'm going to start off first by reminding myself what the density of reinforced concrete is. Okay? I'm going to pick it as density (25 kilonewtons per cubic meter). Okay? I've chosen this as the value for the density of reinforced concrete. Now that I know this value, I have to now find what the volume is of this setup so I can multiply the two to get a force. So what I'm going to do is first I'm going to find the volume of this pier, the cylindrical pier, and the volume of the cylinder is the area of the circle times the height of the cylinder. So the area of the circle is pi r squared. We have the diameter, so we have to divide this by 2. So let's do that, okay? Area, cylinder, it's going to be pi r squared times the length, or the height of the cylinder. I think I call it h here. Okay? And a reminder that this is radius, not diameter. So if you're given diameter, you have to divide that by 2. Now, I'm going to have some forethought, and I'm going to look forward to what's happening, okay? All of this is in millimeters. This is all given in millimeters. But the density here is in meters cubed, right? So whatever volume we multiply by this has to match whatever units we have here. So I'm going to think ahead, and I'm going to do this all in meters, not in millimeters, right? So I don't forget about converting my units. So I'm going to remind myself that the radius is going to be 0.1 meters, right? 200 millimeters divided by 2 converted to meters, 0.1. The height is going to be, if this is 1200 millimeters, then it's 1.2 meters. So this should be volume of the cylinder. So that, when I calculate this out, I think best 2 out of 3, I got 0.038 cubic meters. Check it, best 2 out of 3. Make sure I didn't make a mistake. Okay, so that's the volume of the cylinder. Let's find out the volume of that pad. Okay, volume of that pad is going to be the area times the height. So this dimension times that dimension times that dimension. Again, I'm going to think ahead and use these dimensions in meters, right? Because I want to multiply by this. This has meters here, so meters. So again, that's going to be length times width times height, or depth. So 1.234 meters for the length, 1.234 meters for the width, and the height, since it's 300 millimeters, it's 0.300 meters. When I multiply this out, best 2 out of 3 times, I get 0.457 meters cubed. Okay? So now I have the volume of the pad, the volume of the cylinder. If I add up these two volumes and multiply it by the density, I should get the weight, the force of that pad. So let's do that. 25 kilonewtons per meter times 0.038 meters cubed plus 0.457 meters cubed. What we get from this is, I think best 2 out of 3, I got 12.357 kilonewtons, which is good, right? The meters cubed and meters cubed cancels out. We're left with kilonewtons, which is the right unit for force. That's what weight is, right? It's the force on Earth caused by gravity. Okay, so I'm just going to make a note of that here. That's this value right here, 375. So I made a mistake here. This is 12.375. Right, so always make sure best 2 out of 3, best 3 out of 5. Okay. So now that we have this set up, we can proceed with our next step. And to make things a bit more clear, I'm going to erase this so I can use this space to finish my calculation. Lovely. So now we have a balance here between these applied forces, 163 kilonewtons from the building above, 12.375, which is the weight or the force imparted just by the self-weight of the concrete structure, must be balanced out by the bearing capacity of the soil. Otherwise, if this is more than that, the building will sink. The soil can't push back up enough. So I'm going to remind myself then, just like we did with example number 1, the bearing capacity of soil. Do you remember the formula for that? Bearing capacity of soil is equal to the force applied on the soil divided by the area on which you're applying this force. Now here's the interesting thing. We have the force being applied on the soil, right? It's these two. We also can figure out what the area is over which this force is being applied. It's the underside of the pad, right? Length times width. So, if we put those values in here, we can then calculate the required minimum bearing capacity of the soil. And then we can go back to this table and see which one of those soil profiles give us the minimum required. Let's do that. All right. The force at the numerator is 163 kilonewtons. So that's from the building, plus 12.375. Okay? Because in this case, we've been told that the force of the building is only up to, but not including, the pier and the pad. And then the area. The area is this, length times width. So I'm going to do this in meters again, because we want to get an answer in kPa. Right, go back to example number 1 to see where this is coming from, because kPa is the units that are in this table, and kPa is kilonewtons per meter squared. All right, so the area is 1.234 meters times 1.234 meters. So if I solve this and I do it correctly, I get 115.169 kPa. Best 2 out of 3 times. See if you can get the same number. Okay? I did it all in one shot, but maybe it takes you a couple of steps to do it. No problem. Okay, now I have, this here is the expected bearing capacity of my soil, right? That's what we expect this to be. This here is the smallest value that we can have here, so that these two balance out, given these dimensions. So then, let's go here in table 9.4.4.1 and see which soil gives us those values. So that's what I did. I grabbed that table for the Ontario Building Code, Part 9, and I look for anything that is bigger than this. And I find a few, right? Just off the top of my head, I'm seeing dense or compact sand or gravel at 150 kPa, stiff clay at 150 kPa, and then there's till, clay shale, and sound rock that are even larger than that. So typically in engineering, you're looking to be as close as possible to your values, but not too much more, within a certain factor of safety. Now that factor of safety can be huge, or it can be small, depending on the situation, but that's beyond the scope of this course. So what I'm looking for is the closest value from this table that is larger than this. And I get it with either dense or compact sand or gravel at 150 kPa. So from table 9.4.4.1, sand or gravel dense or compact at 150 kPa. And I think the other one was stiff clay at 150 kPa. Okay? So either one works in this case. Now, to be fair, you could pick some of the other ones, which are much larger, but don't forget, in engineering, then, in real life, and if you remember, there's the cost associated with this, right? So as long as you're looking to ensure the right amount of safety, then you have to also consider the cost, right? Because if you can't afford to do something, you actually cannot do it, no matter how good it is. So in this case, either one of these would work. So the way I would answer is this. Either this or that works. Okay, so in this case, this value would be 150 kPa from either of these values here. Okay? So then make sure you check out the other examples that we have. I think there's example number 1 and 2, as well as the main lecture linked for you at the bottom. I hope these are helpful to you. I want to thank you so much for your time. Take care and have a lovely day.